Good day, everyone. On behalf of Cambridge Health Tech Institute's Global Web Symposia Series and our sponsor, REDSHIFTbio, I'd like to welcome you to using microfluidic modulation spectroscopy to monitor protein misfolds and structural similarity. My name is Elizabeth Lamb, and I'm the host and technical director for today's event. I'd like to introduce our first presenter for today. He is Jeff Zonderman, Chief Compliance Officer for REDSHIFTbio. Welcome, Jeff. The presenter ball is yours.
Thank you very much. I would like to thank everyone for joining our webinar today. At PEGS this year in May, REDSHIFTbio launched the AQS protein analysis system. Today, our CTO, Eugene Ma, will give some background on the instrument, its capabilities, and software, in preface to give you context on the presentation that Brent Kendrick, founder and VP of R&D at Elion Labs, will present on some of the measurements we've made looking at proteins and how they are affected by different conditions. Hence the title, Using Microfluidic Modulation Spectroscopy to Monitor Protein Misfold and Structural Similarity. So thank you very much, and with that I will hand the ball over to Eugene Ma to take you through the first set of slides. Eugene?
Thanks, Jeff. As he said, I hope to present some primer slides here, give you a little background into the technique that you'll hear about in Brent's section of the webinar. So with that, let me jump right in. So as I'm sure many of you in the audience are familiar with, the biophysical characterization of proteins is obviously a very, very important thing in drug development. Many tools exist today. Many of you have these tools in your own labs, and I'm sure you're very familiar with them. For protein structure, we have CD and FTIR, and I should say this is just a subset. It's not meant to be comprehensive at all. For DSC, we have, for stability, we have DSC, for example, tools for aggregation like SEC, and quantitation tools as well. So these tools obviously exist, but industry is always pushing us forward, demanding wider concentration ranges, better sensitivity, the ability to extract better, more actionable data. You want to have confidence in your data so that you can move forward with assuredness. And there's more and more, there's a push for simplification of your workflow, not just in the measurement, but also in the analysis itself. I want to discuss mid-infrared spectroscopy, which is what our technique is based on. So for those of you who are not familiar with IR, it's probing the backbone here of your primary structure. It's looking specifically at the carbonyl bond, which expresses itself in what's referred to as the Amide I band. And this technique has been around since the mid-1980s. It's long recognized as a powerful technique, but information itself that comes from the IR spectrum isn't really able to be fully exploited due to constraints in the current tool set. And you'll hear about that in more detail in subsequent slides. Specifically, the process itself tends to be rather manual. You have to perform very, very careful background subtractions, and these tend to limit the sensitivity of the method. So at REDSHIFTbio, we had particular expertise in a couple new technologies which we have integrated into a new technical platform, which we call Microfluidic Modulation Spectroscopy, or MMS. So on this slide, I will just go through the basics of how this works. On the right side, here you see a schematic showing what is essentially absorbance spectroscopy. We begin with a laser source instead of a glow bar, so we have a lot more light. On the other side, we have a detector, and because of how much signal we have, we do not need a liquid nitrogen cooled detector. In the middle, we have a microfluidic cell. It's a flow cell with two inputs. On the animation below, you can see there's a reference channel on the left, which may contain your buffer. We have a sample channel on the right, which might be your protein of interest in that buffer. And the two fluids are modulated very quickly. We typically run anywhere between 1 to 5 hertz. And what this is essentially doing is it's allowing us to perform very, very rapid background subtraction in an automated fashion. So it's very consistent, very repeatable. And because we have so much light, we're actually able to capture enough signal in that brief time window. So it's really this combination of a very, very bright source in our tunable mid-infrared laser combined with microfluidic referencing that allows us to take very sensitive measurements, looking at not just low concentrations, but also very high concentrations, which I'll discuss shortly. On top of all that, we've included a layer of advanced analytics that helps us automate the processing of that data. So at PEGS, we introduced a new instrument, which is based on this MMS platform. And here, just a quick overview of some of its capabilities. So it has over 20 times higher sensitivity than traditional IR tools. It measures secondary structure for protein concentrations from 0.1 mg per mil to an excess of 200. It features an automated multi-sample capability for walk-away operation. It streamlines not just the measurement, but also the spectral analysis, and I'll spend a slide or two just walking you through that. And it captures 5 key measurements here that many development labs are interested in. We look at aggregation, quantitation, stability, similarity, and of course, structure. This is just a sanity check showing computational model and empirical data, looking at traditional IR tools shown in the blue and black curves versus MMS shown in the red curve. The axes here on the y-axis, we have sensitivity on a log scale, so lower is better. The x-axis is the cell path length in microns. And what you'll see here is that for traditional tools, IR tools, the optimal sensitivity occurs here at the saddle point, and that's usually single-digit microns. For MMS, that shifts lower and to the right. So we're able to operate typically around 25, 26 microns in path length. That gives us a lot more signal. It actually also allows us or facilitates flow through our cell. So we can look at more viscous samples and higher concentrations. And you'll see that we also get about 20x improvement in sensitivity. The markers shown on the plot also indicate the actual experimentally obtained values. So they line up very nicely with our predicted values. On the right, we're just looking at baseline drift. The gray curve is what happens when you take a measurement at time t0 and do background subtraction against it. And you'll see that after about a minute and a half, it's already beyond the peak-to-peak variation of the signal noise. And this just tells you how hard it is to take a very clean background measurement, in particular when the measurement time exceeds about a minute. The blue curve shows our modulated background subtraction, so it's essentially flat over time because we're able to take this on the order of faster than a second. This one slide just shows you actual data we took on BSA. We are looking at 200 mg per mil all the way down to 0.1. You can see the as measured data here on the left. The middle shows our standards curve here. It's very, very well behaved across that full range. And the plot on the right shows you our secondary structure. We break it down into 3 motifs here: extended states, beta turn, and alpha helix. And you can see it's very consistent. The one outlier might be the dark blue here, which is the edge of our spec range at 0.1 mg per mil. Then just a few quick words here on our analytics. Here we are actually looking at some scrub data from a collaboration we did with a biopharma. They had a fusion protein they were looking at, and there was some thermal stress that was performed on this protein and quenched. The data, or the proteins here, were at 1 mg per mil. And the first plot is our differential measurement. you can already see, even without any processing, we can clearly see that there was change in the spectral signature of these proteins. We back out the buffer, do a buffer subtraction, we get the curve shown in the upper right. We can perform quantitation, and the plot is shown here. The blue curve is a standard IgG. The red marker here is the mAb fragment. So similar but not identical, to be expected. This is where the data gets more interesting and where people typically want to spend their time analyzing. On the first plot in the upper left, we generate a second derivative curve from the as measured spectra. If you follow the top path here, you will see that you can run a spectral difference curve, and you'll see that the changes are particularly strong at around 1640 wave numbers, which is associated with beta sheet. Also something down around here about 1625. We can track the individual spectral components with the stressor on the x-axis here. This is basically stress temperature, and you get a classic sort of sigmoidal profile here. And we can see how those spectral features change as a function of thermal stress. Another approach many people like to take is shown in the lower path here. The second derivative is normalized and baseline to give you what's referred to as an area of overlap plot. Brent is very familiar with this technique since he's an author. And we can run a Gaussian fit on each of those spectra, and you see an example here. Each of those Gaussian curves is assigned a secondary structural motif, and we can map those out to get a sense of the structure and how it changes with, in this case, thermal stress. So you can see that with this particular protein, there is a change in the parallel beta sheet here. It's actually blue is room temperature and cool, and the red or dark brown is the higher temperature samples, and you can see that there's a loss in parallel beta sheet with an increase here in anti-parallel beta sheet, and this is typically associated with intermolecular beta sheet, and so we expect there's probably some aggregation going on in this particular sample. So that gives you a sense of some of the analytics that are built into this tool. I'll just quickly sum up that we believe microfluidic modulation spectroscopy is really an ideal technique for characterizing proteins. It performs 5 key protein structural measurements, which I mentioned to you earlier. We've verified this against orthogonal measurements of X-ray diffraction, FTIR, CD, and we've observed in our own measurements more than 20 times greater sensitivity with a much wider concentration range. We validated this against real-world experiments performed with a number of collaborators, both in academia as well as in industry, with particular attention to high concentration ranges and looking for very, very small structural changes as well. And I'll just say that our collaborations are continuing this year, and we will have our multi-sample analyzer available later this year. You'll be hearing more about some of its capabilities in the section that's going to follow that Brett will go through. And with that, I'll hand it over.
Good morning, everyone. Well, I was contacted by Redshift a few years ago regarding their developments of a new FTIR or IR MMS instrument. And it intrigued me because I've been working on protein structural characterization for over 20 years, and mainly in the context of biopharmaceutical development. And what has kind of plagued our utilization of spectroscopy tools has been their relatively low sensitivity to detecting structural changes and degradation relative to other techniques such as HPLC methods and other techniques, but we still tend to use them just to confirm that we have no gross changes in protein secondary and tertiary structures. And when I heard from Redshift about developing a new IR instrument, which had potential for 2 things. One is better sensitivity to structural changes, as well as the ability to go to lower protein concentrations. I became interested in working with them further, and As you see, we have some really exciting developments in both of those areas. So the objective here that we're going to cover are looking at a couple different common spectral techniques, IR and CD spectroscopy, that tend to be the workhorse in biopharmaceutical industry to look at structure of proteins. And we look at them in the context of a few things. One is whenever we make a manufacturing change in our production process, we have to demonstrate that the change in the manufacturing process hasn't resulted in a change in our protein structure. And IR is a common tool to do that. We also, in the context of biosimilars development, want to compare structures of drugs made from different manufacturing processes. So we'll compare the innovator's drug structure to the structure of the biosimilar company's structure. We also use it as a tool commonly during formulation development to pick the formulation that has the least impact on the native structure of the drug, both unstressed and under stress conditions, and optimize these protein formulations against structural impurities that might form, like misfolds and aggregates. So what we're going to focus here on this study is using a model system that creates quote-unquote misfolded species spiked in at very precise levels that we can control and assess the detectability of these misfolded species into a monoclonal antibody system. So briefly, the instrumentation that we're using is the traditional Fourier transform infrared spectroscopy, and we optimize this measurement using liquid nitrogen-cooled MCT detector, 128 consecutive scans running at 20 mg per mil, and focused on the Amide I region. The MMS instrument, you see, was operated at ambient temperature using the 23.8 micron path length and 31 discrete wave numbers across the Amide I band were measured. And then for CD, the sweet spot for the secondary structure measurements were run at 1 mg per mil, which maximizes the ability to measure spectral features of CD, and the rest of the instrument parameters are provided there. So our model system, we wanted to kind of maximize the detectability of structural misfolds, so to speak. So, and we wanted to use a relevant system as well. So our system was primarily an IgG1 monoclonal antibody spiked in with a misfold impurity. And for this, we used bovine serum albumin. And the reason we chose BSA was it's almost entirely alpha-helical structure, whereas IgG1 is mostly beta strand, over 86% beta strand. And so we wanted to choose a system with a very different secondary structure, spike that in, and see at what level we could detect a change. Obviously, if we had spiked in a beta sheet structure, the detectability of the misfold would be less. And so we wanted to create a kind of best case scenario for detecting structural misfolds. Now, with traditional IR, I want to cover a couple specific things that impact the precision of this measurement, because what we're getting at is what is the detectability of these procedures to find misfolds. And so with IR, I want to spend just a couple slides on talking about the areas that cause error in this analysis and ones that, with the other technique, MMS, has some controls around that improve the precision of the technique. So with IR, one of the complications is it seems very subtle, where you have very slight differences in absorbance. And so this is the same sample run 3 times. And on the left side, you can see that in the raw absorbance spectra that's non-buffer subtracted, you get a very subtle shift or lower absorbance of the first replicate there in blue compared to the buffer in yellow. And then the red and the gray trace overlay almost identically. And so it seems like a very minor difference in absorbance. And when you do the subtraction to the buffer subtracted spectra, you can see that that results in a lower overall absorbance as you'd expect. in the amide I band. And this can this slight variability here can result in a measured difference in the spectral similarity. It complicates the ability to detect small differences in spectral structures. We did a little bit of investigation with the FTIR to figure out what was causing this difference in absorbance. It's very common. It happens across replicates and across samples. And we wanted to, since we use a flow cell setup, we wanted to just make sure that the path length in the flow cell wasn't experiencing minor changes due to injecting our sample with a syringe and creating a pressure on the cell and potentially increasing the path length. We ruled out path length changes by measuring the path length with an interference pattern, and it was very consistent at 8.4 microns. So what we suspect is that these flow cells are very sensitive to just slight presence of dust that can create air bubbles in your flow cell, and these can be even microscopic, but can lead to subtle differences in the absorptivity of your sample and create apparent structural differences where there really aren't any. Okay, so now I want to shift a little bit and talk about how do we measure structural differences or spectral differences. And there's a number of mathematical techniques that you can use. I'm going to show three that we tend to focus on at Elion and KBI. The first is this area of overlap, one where it's a very intuitive way to look at structural differences or spectral differences. You simply take the amide I region, and in this case, IgG1 is shown in blue, BSA is shown in orange, and gray is the region of similarity of the two bands. And if you area normalize both of these spectra, the area under the curve to 1.0, then that gray area is a fraction of 1.0, and that's 0.84 in this case. And so you can claim that there's about a 84% spectral similarity just by area of overlap. There's a couple other techniques that we tend to use. One is called DCA, where you take the derivative. It's a numerical derivative of the Y values from spectrum 1 and spectrum 2, or the intensity values. And those are normalized with the sum there. And this is found in the Omnic QC Compare software, and we've used it in our labs to correlate and measure spectral differences as well. And then finally, the weighted spectral difference, which takes a weight of the intensity of the spectra at any one point, divides it by the average intensity of the entire spectra, and multiplies it by the square of the differences in the intensities of each data point across the spectra. And this gives you a factor that we term weighted spectral difference, and perfect correlation would be a weighted spectral difference of 0, and as spectral changes increase, then you get a higher weighted spectral difference number. We also tend to utilize second derivative spectroscopy, so it's just simply taking the amide I spectra and taking the second derivative, sometimes applying a slight smoothing function to get rid of noise, and compare the spectral differences that way. And that has some advantages, which I'll talk about in a little bit, where you have improved spectral resolution of bands, and it accentuates the differences in spectral features, and it can actually improve your sensitivity to detecting spectral differences. Okay, finally, in terms of the data analysis, I wanted to talk about how do we quantify the limits of these techniques? How low of a structural difference can we detect? And so for this, we use the ICH guideline Q2R1. ICH stands for International Conference on Harmonization. It's basically a regulatory body that has published some guidelines on how to do a variety of things in biopharmaceutical development. In this case, it's the quantitation limit, QL, or also known as LOQ, limit of quantitation. Use those two terms interchangeably. And the quantitation limit is expressed as 10 times the standard deviation of the instrument response divided by a slope of the calibration curve. And this allows you to say at how low of a concentration or percent impurity can we statistically say that we can quantify difference in that? And so this is valuable for us, where we can essentially look across spectroscopic techniques and say, you know, does one have better precision than another, and can one detect down to lower levels of impurities than another technique? The standard deviation of y is given, standard formula there at the bottom. And we calculate that using Microsoft Excel in our case. And you can, if you're interested in doing this yourself, I've just provided a slide here on how to do that using the LinEst array to get your standard deviation of y and the slope, and then you simply calculate LOQ by 10 times standard deviation of y divided by the slope. And so for this data set, you can see a standard deviation of 1.0 times 10 to the minus fifth divided by the slope gives us an LOQ of 0.76 in the data set shown in the upper left. So for traditional IR, it does require some data processing to improve the precision of the technique. And one reason we need to do additional data processing, in this case, we will area normalize the Amide I region, is due to those subtle differences in concentration that I showed earlier. And so we'll apply, in this case, this is a second derivative. I'll come back to the Amide I in a minute. But we'll apply an area normalization algorithm under the curve, area under the curve, to just normalize those all to an area of 1. And you can see the benefit of doing that, where before the area normalization, we have a very poor R squared, comparing as we spike in BSA at higher and higher levels, up to 10%. We see very poor correlation in terms of the weighted spectral difference. R squared is about 0.45. Then when you do area normalize, you get a noticeable slope with a better R squared of about 0.77. And at this point, we can start to say we have some confidence that we can measure some degree of spectral difference as we spike in BSA from 0 to 10%. Notice that DCA, the derivative correlation algorithm, is independent of peak area, so you don't need to area normalize for DCA while you do for weighted spectral difference. And that's because it kind of has a built-in correction factor that takes the intensities and divides it through by the overall intensities to weight out that. So that's a nice feature of DCA. One drawback of the DCA is it's not a linear change. As you can see, it's a quadratic function, and it's actually fairly flat at low levels of the spike impurity. So at first blush, it appears that it may have some limitations in terms of going to very low levels of an impurity to detect it, as it tends to plateau out at very low concentrations. So this is just comparing, the last slide was FTIR data, this is the MMS data, and you can see right away that the data looks cleaner. We'll come back to that in a minute. The main point here is that this technique also benefits somewhat from area normalization. The R square is pretty good without area normalization, which suggests that the instrument is very robust in terms of not having differences in overall absorptivity due to these apparent microbubbles that happen in the traditional FTIR flow cell. The R squared is 0.9965 when you don't area normalize. And when you do area normalize, you get a better R squared of 0.9997. Okay, so I want to touch on why we take the second derivative as part of our spectral processing. And the main reason is that it's a band narrowing technique that doesn't have much in the way of subjectivity. So you can take a second derivative. Everybody, you know, kind of across the world will take the second derivative in the same way, and will lead to, if we give somebody, you know, two different people at two different companies, for example, the same spectra, they can both take the second derivative and have the same results. Whereas other band narrowing techniques, such as Fourier self-deconvolution, have a fair number of subjective parameters that go into them, and depending on those parameters, you can get very different results. So we like the second derivative because it's a fairly objective process. And the reason we do it is you can see that you get better band narrowing, which allows you to pick out spectral features that are different across the Amide I spectra. So on the left, we have a set of data, 3 replicates, in this case, a 6% BSA spiked into IgG1 sample. And you can see there's some variability there in the Amide I spectra. And in the second derivative, we can pop those out, and it actually looks a little more similar by that because it's looking at differences in shape rather than differences in overall intensity. So I want to show you how these different spectral comparison methods look for a given sample type across the Amide I region using MMS. So as I mentioned before, there's different spectral similarity calculations that you can do to measure the similarity or degree of difference between spectra. The first one in the green box at the upper right is this weighted spectral difference technique. And so when we plot BSA spiked into this IgG1 from 0 to 10%, you can see you get a nice linear increase in the weighted spectral difference response. And we can run that LOQ calculation, and it comes out to an LOQ, or limit of quantitation, of 1%, which means that we can statistically and reliably quantitate structural differences down to 1% or less. Or in this case, we could detect a BSA, a structural impurity in this sample down to a level of about 1%. And we can compare that detection or quantitation limit to these other spectral comparison techniques. So the simplest one is probably just looking across the spectra visually and looking for where's the greatest degree of change in the spectra. In this case, it's in the alpha-helical band region at 1656, which would be probably what you would expect since we're spiking in an alpha-helix impurity. You'd expect to see a spectral change at that wave number. And indeed, you know, you can plot the intensity of that wave number at 1656 across your spike levels, and that's shown in the lower left, and that gives you an LOQ very close to the weighted spectral difference of 1.3%. You can plot the area of overlap and get an LOQ of 1.2. And with DCA, you know, we see a nice quadratic decay curve, so to speak. And we are working on an algorithm to pull out LOQ of this quadratic function. It's not as straightforward as doing a linear fit and having a slope, but it's something we're working on. Now, when we compare the Amide I MMS to traditional FTIR, you can see a dramatic improvement in the LOQ. So whereas the traditional FTIR, you can see there's quite a bit of scatter in the data as you spike in BSA. You do get a positive slope, but the LOQ is above 30%. So this tells us for at least Amide I spectral differences, we can't really detect a change, or we wouldn't be able to detect a alpha-helical impurity until it got to levels of 32% or higher, which is pretty gross changes in structure, not a very high resolution technique in this case. Now, compare that to MMS, where the LOQ is much better. You can go down to 1%. Now, this 1% is almost on the order of traditional purity techniques that we use, such as HPLC and CE and SGS-PAGE, where we look for impurities. This is a very high sensitivity technique that can give us detections down to at least 1% in this case. And we can improve things even better or even further by taking the second derivative. As I mentioned, taking the second derivative improves your band resolution. And now it does improve the FTIR detection threshold. So we can go from over 30% to down to 22.7% detection threshold. Still not great, but it does improve the detection threshold for traditional IR. For MMS, now we're well below a 1% threshold, and we can quantitate down to, in this case, 0.76% impurity level. Compare that to CD, which is another traditional technique that we use to look at secondary structure, and a very good technique overall, especially compared to traditional IR, where it has a detection or quantitation limit of 3.7%. You can see even in this case, the MMS offers significant detection threshold of at least 5-fold better than far UV CD. Now, another common technique that is used in the industry is to use ATR, which stands for Attenuated Total Internal Reflectance. And you pair this with an FTIR instrument. And the advantages of this technique are it's very easy to run instead of dealing with a flow cell and cleaning the flow cell between samples and dealing with things like air bubbles that I mentioned before. You just layer your sample, your liquid, on top of this crystal. And you bounce your IR beam across the HL crystal, and a little bit of the wave penetrates into the sample, and you get an IR spectra. And this does have better precision than traditional FTIR. Here you can see we can have an LOQ of about 15.9%. The problem with this is that you're measuring the spectra of a protein that's absorbed, primarily absorbed onto this ATR crystal surface. So you're not measuring bulk solution properties or bulk solution structure as much as what the protein looks like at a surface. And in fact, a lot of people will use ATR to study protein interactions at surfaces. And you can see the distortion that happens in terms of the structure, both for BSA and an IgG1, where for BSA, you're losing alpha-helical content, increasing beta sheet. That's hypothetically due to this absorption where the protein is unfolding and possibly even aggregating at the surface and creating an increase in beta sheet. And this happens also not to as much of an extent, but to some extent for an IgG1 sample. Okay, so and then finally to wrap up, we do have some other potential applications that we're going to look into with MMS. One is that IR and CD are often plagued by interference from excipients, especially common amino acid excipients like histidine are used in protein formulations, and those have a very strong Amide I absorbance due to their amino acids. By IR and by CD, they absorb heavily in the far UV, so they complicate and even limit the ability to detect spectral changes in the presence of these excipients. We also like to use chaotropes such as guanidine to unfold the protein for a variety of reasons in pharmaceutical development. And guanidine also can strongly absorb by IR and CD and limit the ability of those techniques. And we think with MMS, we may have better opportunity to explore structure in the presence of those excipients. We also want to further probe the ability to measure protein structure at low protein concentrations. One of the big drawbacks of FTIR is that you have to run generally at 20 mg per mil or above. And as you saw earlier from Eugene, that we could measure possibly down to even low as, and they have measured down below 1 mg per mil, even as low as 0.1 mg per mil. So we want to investigate the limit of quantitation in samples and in some of these model systems down below 1 mg per mil. We also want to look at other model systems that we can use, and we picked one that would serve as a kind of best case ability to detect structural changes. But we also want to explore other model systems, including spiking in fully denatured proteins, soluble aggregates, and other forms, and see how well we can detect those misfolds. And then finally, the way the system works, it may offer some ways to get at the early reaction rates for hydrogen deuterium exchange and look at early kinetics of this H2D exchange reaction and probe conformational structure using H2D exchange techniques. I want to acknowledge a number of folks at Elion and REDSHIFT for helping with this work over the last few years. Also, a few references for you there at the bottom, especially if you want to explore some of the background on these spectral similarity techniques. And finally, I just want to mention that we have a number of locations at KBI where we can serve your analytical and product development needs.
Thank you very much, Brent and Jeff and Eugene,